Yeah, I guess. Well, we assumed that the Wi-Fi was in. I think it meant. Tu veux utiliser le lien dans YouTube et le dans ton profil YouTube? Non? Okay. I want to do a cooking project, so it's just give me 5 minutes. I know you. Oh, right, yes.
Hello everyone. Welcome to Atlassian. Welcome to the SF WebRTC Meetup, the June edition. We're gonna get started right now. We are live on YouTube for the one who wants the link. It's or tweet the link or whatever. It's on the Twitter account SF WebRTC. Our first, we're gonna get first an intro from Emil, Atlassian, leader of the well-known Jitsi project. Then we're gonna get Kensaku from AT&T. And then hopefully Armen from Dialpad, Uberconference. So first, please welcome Emil, Ivov.
Thanks. I actually wanted to welcome everyone. Thanks for coming. This is the first WebRTC meetup that I am assisting on in SF. So this is super cool. And I just wanted to start with, well, first, welcome to Atlassian. Thanks for coming. The connection between Atlassian and WebRTC passes through the Jitsi.org community, which is an open source project. We became part of Atlassian last year. And since then, Atlassian has graciously continued to develop this project in open source, and the community has grown a lot. Many of you here are actually using Jitsi, for which we're all very happy, and you are all contributing, so thanks for that. As part of this intro, I'm not going to go through all the architectures and benefits of different ways of doing multi-party conferencing. I've personally done that a lot, and many other people have as well, so I'm not going to bore you with that stuff, although I really want to, but I'm not. The important part is that the main WebRTC related piece in the Jitsi project is this open source video router, which allows you to build applications that work exactly the same way as Google Hangouts, for example. Public service announcement, we just made part of this project the Jibri the Jitsi project, which stands for Jitsi Infrastructure for Broadcasting. Jitsi Broadcasting Infrastructure. Well, the real name comes from this barrel that you make alcohol in Bulgarian you call it Jibri, and that's why we decided to call the project that way, because you get drunk. That's how good it is. So you can download it or you can use it on Meet Jitsi, which is our public platform. So far it was meant to be just a demo site for the Jitsi Meet project. And since recently, we've actually started making it a platform for everyone who actually wants to have a very easy way to integrate WebRTC applications in their infrastructure. And just yesterday, actually, what is it today? No, the day before, on Monday, Rocket Chat released their integration of video through the Jitsi website. And again, that's the cool part with open source, that you can either use this platform, you can use a platform that anyone else uses, you can just download it and run it yourself the minute you're not happy with whatever service you're being provided. So with that, I'm going to cut it here, but don't worry, I'll come back and bore you more with this evaluation of simulcast that we have for just a little bit later. And now I'm going to pass the mic to Kensaku from NTT. There you go.
Yeah. Oh, this is mine.
And you leave this actually.
Okay. Hmm? Okay, is it okay? Can you hear me? Can you hear me? Okay. Thank you so much. My name is Ken, and I'm now working at NTT Communications, a Japanese telecom company. And so today in this meetup, I will talk about the testing things about WebRTC for our activities. Let me introduce myself. As I said, my name is Kensaku, but pronunciation of Kensaku is a little bit hard in English words, so that please call me Ken. Ken will find. And as I said, I'm now working at NTT Communication, and until last December, I have worked in Japan, but from last December, I have moved to Silicon Valley area, so that I'm now working in Palo Alto offices. And I'm doing the technical manager of our Synergy Gateway Services, Skyway, and a bunch of community work in Japan. I have done it. And this is an activity for me for recently 3 years. We started Synergy Gateway Services called Skyway mainly in Japan 3 years ago. And from last December, I moved here, and then I'm now doing some collaborative job with Box. So that, and beginning of this month, I deployed some prototype services based on the Box URL API, so that with this URL, you can have a kind of a web conferencing system with Box and Skyway. And so that from now, I will do the presentation about today's topic. Today's topic is testing for the WebRTC. So let me get started with the generic testing for the web application. As you all may know that we need to check our web applications for each browser. And so that, for example, we need to check some web application for the Chrome, Firefox, Opera, Safari, or Edge, maybe Internet Explorer. Yeah. And In the generic web application cases, it is the order is linear. Okay, as you might easily understand. But for the WebRTC cases, we should check peer-to-peer connection between each browser. So it means that, of course, and I think you may know that I removed Safari in this icon. I'm a little bit disappointed with the WWC. Okay, anyway. But, okay. So check each combination, we should check for the testing so that it means order of square. Yeah. It is a tremendous number compared to the linear. And also, this is not enough for the WebRTC testing case because such services are affected not only such browser pairs, but also a network condition of what type of NAT they are using, proxy, and bandwidth, the latency or something else. It affects on the services so that we need to check for the testing stations. So it means that for the WebRTC testing case, compared to the generic web applications, we have to do the tremendous number of the test. It is quite hard. So it means exponential. The order of exponential we have to do for the testing cases. And I think that for such a cases, building testing environment from a scratch is not a good idea. My opinion is that to have a framework for the testing for the WebRTC cases, so that our team Skyway built in-house environment for the WebRTC testing in our cloud environment. This is a figure of the testing environment. This green line shows each router network, and we set each client on the downside and the server system on the other side. And between up and the downside, so we set up 9 types of maps in our cloud. And then doing some kinds of easy WebRTC test, transferring video or data or something else for each combination of the browser and the NAT type. And we made a dashboard to show the result of the test cases. And I will show you the dashboard. Okay. Of the WebRTC test result. I cannot have network connections. Okay, some network troubles happen, so that, okay, I will skip the demonstration. Okay. It's okay. It's okay. Okay, happy I can access my dashboard pages. This blocks shows represents that each browser pairs test result, and green shows the success, and of course red shows the fail. And I think you may find that each browser pair has small pieces of boxes, and these small pieces boxes represent that each type of NAT for those client users. And for example, if you create some boxes, I think long will be displayed here, but okay, some trouble is happening, but so I will skip this demonstration. Okay. So in this way, we can check the WebRTC application testing result for each environment. And I will notice you that we implement each type of nut from scratch. And in the IETF, RFC, logically there is a 9 type of nuts so that we implement it from scratch. But most cases, most WebRTC cases, those 4 types of nut we should check. And I explained our activity for the WebRTC testing last year. But I felt that we felt that our activity has issues because this test environment is quite specific for our systems area. And for example, this test environment is built on top of our cloud system. And for the signaling services and the servers, we use our servers. It is not generic. And that is that for building such an environment and doing a test, there are a lot of components inside, but each component is quite banded deeply. So that it is not good to use generic use cases. So that we are now moving to next steps. Move our test environment to open source basis. So it requires some refactoring our best practices and other features we are implemented. And our recent 3 or 4 months we have done for the project, for the open source basis, so that I will show you current status of our test framework. We refactored our test environment so that we set up as a framework. And each component is divided 4 phases. 4 phases. One is bootstrap, one is configure, and the other is bootstrap. And I will explain each phases from now on. In the bootstrap phases, our framework supporting Amazon VP, AWS VPC, and with the CloudFormation, each virtual machines are installed inside the VPC for the in-house test environment. And then next phase is configuration. We use Ansible to set up each server software on top of the virtual machines, each browser on top of virtual machines, and each net on top of virtual machines with Ansible. And then orchestrate server control phases. This component starts each server applications. And after that, testing will begin with the server. And we also set up with some different server inside the framework and different application inside framework and different test cases inside framework and in general cases are solved. For the specific cases for each developers and each company, update those 4 phases now. For example, if you want to change the signaling server, change signaling server in the bootstrap phases and configure phases. If you want to install SFE or something else, append in the bootstrap. That all depends on you. But we are now facing the problem. Actually, originally we are planning that to open source basics development in this season. But current status is we can do this because a lot of errors now happen in these days. And we are now investigating the reason why such errors are happening. One is driver mismatch or something else. And one is that because we are not using T2.micro for the AWS EC2, that will be the reason. But we need to investigate what's the reason so that we are not doing so. And so that after investigation, we will do our framework project into the open source basics. And I think it will be in this fall or winter. Actually, the repository is now the private repository, but we will make it change as a private repository. And I think I can have an opportunity to explain what's going on when the public open source basis is finished. And I think you will give me some opportunity. Okay. And that is all my presentation. Thank you so much. Question? Okay. So I know this is that can you? Okay. Yeah. Oops, sorry. So this is a long while the testing period, and not only such a long, but also we gathering the packet capturing data in the NAT boxes. And based on such stored packet capturing data, this dashboard supporting some kinds of animation. Okay, after 1 or 2 minutes it will appear, so that during the waiting time, I can have some question if someone has it.
How did you test the concept? How did you concept?
Okay. In this framework, we are now using Potan. Okay, and so that of course you can change the tensor for your own basis. Yeah. As a reference server, we set that to Potan. There is no internet connection.
I disconnect.
Okay. I hope it works. Okay. So based on such a packet capturing data, such animation is now I like a shooting game. People get what packet transaction is where the scenario packets. And in this case, TAN server is now used so that such a UDP traffic and TCP traffic and going through TAN servers. Yeah, and every test scenario, we can check such animation within our framework.
Is this visualization also part of the open source?
Yeah, of course, yes. We will deploy as open source basis. Please enjoy it.
That's the best part.
Thank you so much.
What do you guys use to generate the animation? Do you make it off of PCAPs or?
Yeah, of course. Okay. The data is based on the PCAP data.
So there's something that where you input a PCAP and you get out an animation.
Actually.
Perfect.
I think some modification will be required, but we need to check the PP side. But basically, it's okay.
It's okay. Can you talk a little bit about the error cases that we saw, the red dots?
Uh,
Are they mostly due to the same reason or wildly different reasons?
Sure. Of course, there is a lot of reason why such red cases happen. Sometimes creating peer connection failed, and sometimes the video stream make black. Okay. So what the reason for the red cases depends on the test scenarios. What developer make this in the scenarios matters. Yeah. But for those cases are now included in the red achievements. Okay.
What cross-browser tests work the best, and which ones work worse?
I don't want to say that what is the best case in this phase because it depends on the WebDriver's compatibilities. But I think that Chrome stable is the best match for the WebDriver so that we can have a good result. And nowadays, Firefox have a program with a combination of the WebDriver so that in current status we can do the range test with Firefox. Yeah, but I think it will be addressed, and after that, I can have a clear answer for your questions. So,
Good?
George, you remember your part of this presentation? Right. So, as I said earlier, one of the main things that we do in relation to WebRTC within the GT.org project is a video router. And a video router is, let me do a quick poll. How many of you are familiar with the MCU and SFU abbreviations? That's awesome, okay. So does anyone want to summarize in a single sentence what the difference between an MCU and an SFU is? I'm sorry?
Matching the video or no?
Yeah. Well, I mean, actually, let me ask in a different way. Would anyone point out a single advantage of using an MCU in a conference scenario as opposed to an SFU?
Bandwidth usage?
I love that. Bandwidth is, thank you. That's exactly what I wanted to hear. That's exactly what I obviously disagree. And then obviously I'm completely unbiased. But I really am. So the main idea behind an SFU, as you all know, is we don't do anything with the media, we just route packets. And every time you say this, and people who build real-time communications applications would go, oh, you mean that if I'm a mobile device, it's just going to send me packets that are being sent from everyone else? Are you crazy? This is never going to work for me. And yeah, that's the bandwidth advantage that many of you mentioned. And everyone thinks an MCU is going to tighten your packets and make them in a nice, tidy, small stream that everyone can handle. And if you're a mobile device, a friendly MCU would make a really small, compact stream that you can eat, and life would be beautiful. Now, The thing is that SFUs are slightly smarter than just blindly forwarding packets. I still think that there's reasons to use MCUs, but that's primarily if you want to talk to legacy devices that do not support multiple streams. In any case, bandwidth is not a reason to make your choice one way or another. Here's why. Now, there's numerous techniques that SFUs use in order to make sure that the bandwidth that you get out of an SFU is going to be pretty much the same in case you were using an MCU as well. And the reason that this works, the reason they can make it work is because they try to use various aspects of the applications and make some assumptions that would help them be smarter about the traffic that they route. Now, here's an example. Here's two screenshots of the GTMeet application. And the reason I'm pointing them out is because there's many conferencing applications out there. You often have one on-stage speaker and then multiple thumbnails. This is very often the case. Either you have that or you have the Brady Bunch scenario, which I'm less interested in because recently it's not being that popular for obvious reasons. Now, in this scenario, you're thinking, all of these guys here, I don't need to get in HD. So why would an SFU send me all the packets from these streams? And the answer is that it wouldn't. And then someone might say, well, how would it not send me all the packets given that it's not touching media? It's not going to be able to shrink down these streams and make them smaller, right? Well, that's true. It's not going to do that, but what it's going to do is make the clients do the job for the SFU. This approach and this technique that I'm showing here is called simulcast. And the way that it works is every client would encode their video in multiple resolutions. And all of these will be sent up to the SFU, and the SFU would only forward one of them. Which one depends on various things. First of all, it depends on whether or not you can afford to get the highest quality layer. It depends on whether or not you're actually watching the highest quality layer, whether you're currently rendering that stream as the lower quality layer. The important part is that these encodings happen in the client, so there's no heavy lifting in the server. And so there are two questions that might arise from this. First of all, what is the impact on the client? Because now you're suddenly making it encode 3 streams and not 1. And as we all know, encoding is sort of heavy. And secondly, the server is now handling more traffic. Does that mean that it's actually paying the cost? That might make it less of an interesting choice. So George and Boris have been working on an evaluation of all of these questions during the past several weeks. And we're soon going to publish a paper with all the results, but this is just a sneak preview of their simulcast evaluation. So this is the first comparison chart that you get here. With the red graph, we see how bandwidth usage grows as you add participants to a conference. If you're not doing simulcast, this is what you get. Obviously, you get a geometric progression or close to that because you're every time you add someone, you are increasing the number of demultiplication of the streams by 1. So basically, if you have 3 participants, each and every one of them is getting 2 streams. If you have 10 participants, each and every one of them are getting 9 streams. So it's if you're not doing simulcast, an SFU can quickly become overwhelmed with traffic. Now, if you do turn on simulcast, you get pretty much a linear progression, which is the reason is that every time you add someone else, we are only adding a small footprint in terms of bandwidth utilization. Now, there are other techniques when using SFUs that would actually make that even flat at a certain point because, such as last 10, for example, because certain videos will completely be discarded. This is in the scenario where every video stream has to be forwarded in one shape or another. So, yes?
It's outgoing integrate, right?
Yes. So, moving on. Next question would be, what impact does that have on CPU utilization? Now, interestingly, you would have thought that because the main CPU utilization factor in an SFU is encryption and the need to decrypt and re-encrypt all the traffic, you would think that naturally CPU utilization should be proportional and pretty much you should have the same graph. Well, it turns out that not really. At least not in our implementation, that was not the case. So this looked interesting. Basically in simulcast and in non-simulcast, we get the same CPU utilization, even though that the traffic with simulcast is dramatically lower. So we were wondering why that was. And it's actually due to the fact that encryption is not really only a function of bitrate. It's also a function of how often do you call your decrypt functions. And it's also a function of how you copy or how you move your bytes through your chain on the bridge. So it turns out that originally we were a little bit naive about simulcast. One interesting thing to understand about SFUs is that they would not send the same stuff to everyone. Like someone can get a no in high quality, but I might have clicked on George and I might be watching him on high quality. So it's really per destination that the SFU decides, am I going to forward this guy in high quality or in low quality? So the point I'm trying to make is that this choice is being made very late in the chain, on the bridge, in the chain of it's not an encoding chain, but in the transformation chain. So basically, all the packets that we were getting with simulcast were going through decryption. They were going through all the places where they were actually causing CPU utilization, just as if it wasn't, just as if we were doing non-simulcast. So, or at least similar to that. So what we thought, well, there are a bunch of scenarios where we know that no one is currently watching or knowing high quality because I'm speaking and everyone is watching me on the stage. So I'm being forwarded to everyone in high quality. And if that's the case, then the video bridge, the SFU shouldn't even try to decrypt our node stream and it should just drop it. And once we implemented that, this is what you get. So there was a noticeable improvement in the CPU utilization when we did that drop. So that was pretty cool. This is a note to anyone who's I know that there are a few new SFU projects, so if anyone is working on that, that's a good thing to consider when you're doing simulcast. Now, this is the part of the simulcast evaluation that covers the server side, and really the more interesting stuff is happening on the client side. This is where most of the benefits are, so I'm going to leave that part of the presentation to George.
Hi. So the client can be seen as a sender or as a receiver of simulcast. As a sender, it does have some. We do have some penalties, like since you are encoding and you're sending 3 streams, you're going to stream. You're going to stream. You're going to use more outgoing bandwidth. We use a specific implementation, like the WebRTC.org implementation, because we don't have any other implementations anyway. Well, you do. I'm sorry, I shouldn't. You have the open WebRTC implementation, but we have evaluated the WebRTC.org implementation, and the target bit rates for when you're doing simulcast is you allocate 150 kilobits for the low quality stream, 500 kilobits per second for the middle quality, 360p actually stream, and 2.5 megabits for the HD layer. When you're not doing simulcast, well, you only have the HD layer, which is 2.5 megabits, and when you're doing simulcast, you're streaming the addition of those two streams, which is 3.15 megabits. So you have you're penalizing the sender a little bit with that respect. You do have a negligible, we're going to see that in the next graph, increase in the CPU use because you're encoding 3 streams as opposed to 1, but there are many tricks that you can implement in the encoder that can mitigate this penalty. there are CPU optimizations that you can do there, and then you also have some additional complexity that you have to handle on the server because, well, simulcast hasn't been quite yet standardized. And for example, based on the network conditions and on the load of the machine, the high quality stream might get dropped, or even even both the high quality stream and the middle layer quality stream might be dropped. So you have to do some handling there to detect those drops at the server, so that you can, well, when the high quality stream disappears, the server should forward at least the low quality stream. So there is some handling that the server, some complexity that the server needs to handle. So this is the performance penalty that you're paying on the sender with respect to CPU, which is the red one is the non-simulcast case, and the blue one is the simulcast case. The mean is just slightly above the mean of the simulcast CPU utilization is just slightly above the non-simulcast case. So you basically don't have any CPU penalty because you're doing simulcast on the sender. So this is good news, because on the MCU, in order to do all the mixing and all the transcoding, you're paying quite a lot of stuff in terms of CPU. It's very expensive. Well, when you offload this process on the sender, well, it's basically essentially free. Yeah, so that was the news on the good and the bad stuff on this. If you see the client as a sender, if you see the client as a receiver, when the client is receiving simulcast, so there are a few things that you have to take into consideration. For example, do I have an impact on the quality I am receiving? So we have performed some tests. We're using PSNR as an objective measure of the quality that the receiver is getting. We're going to see that well, simulcast, at least in the WebRTC.org implementation, you also get some temporal scalability, and we're going to see that has some effect on the PSNR results. And this thing, the CPU optimizations that the sender is doing in order to get simulcast for free, in terms of, well, with respect to CPU usage, well, that as well has an impact in the quality that the receiver is getting. But you have some significant advantages, significant gains in bandwidth and in CPU usage at the receiver. Yeah, we have, during our results, our experiments, basically it was very hard to perform experiments for large conferences, for conferences above 10 people without doing simulcast. It was, yeah, if you want to stream HD, it was, yeah, practically impossible, at least in our case. So this is the PSNR results that we get on the receiver. Basically, we have a way to capture frames and have an input frame, and to compare input frames and output frames. The output frames are being captured on the receiver, and the output frames, well, we have a pre-recorded video that we extract frames from, and we do the comparison. So for frame 1 on the sender, we compare frame 1 on the receiver, and we get a PSNR result, which we plot in this chart. You are going to the overall behavior of the chart is controlled by the input file. So you're going to see that, well, we have an input file and it's looping, so that's why you observe the same pattern 3 times, basically. So the red graph represents the PSNR results for the non-simulcast case, and the blue results represent the simulcast case. And as you can see, they're different. We try to understand and explain these differences. In how they're different, so the blue one varies a lot more, and also if you notice, it achieves lower PSNR results with respect to the red one. So we have 2 things that we need to understand. We'll try to explain those. So first, we have deactivated temporal layers for the simulcast, because when you're doing simulcast, the WebRTC.org implementation activates 3 temporal layers. So we remove those temporal layers, and all the variation has gone away. And this is because the WebRTC.org implementation allocates different bit rates to different temporal layers. So, for example, for the high temporal layer, you get high bitrate allocation. But if you remove all the temporal layers, you get the bitrate is being allocated to a single temporal layer. So you remove all this variation. But still, the blue graph is below the red one. Here we're comparing the non-simulcast case with 3 temporal layers and the simulcast case with 3 temporal layers, and they're almost the same, still not exactly the same. And this is because of the motion vector we use, the CPU optimizations that are being done on the sender to achieve cheap simulcast. So you do get a bit less quality, like slightly less quality with when you activate simulcast with this specific implementation. We also have now, the receiver has substantial gains in bitrate, in incoming bitrate. So the red line is, I think I have done a mistake here. Yeah, I think I have done a mistake here. The red line, no, the fact that it's flat is okay, but the fact that it's non-simulcast is not okay. So the red line actually is a simulcast, and it's how much bandwidth you get, how much bitrate the receiver is getting. So the red line is as you increase the participants. So on the x-axis you have the number of participants, and on the y-axis you have the incoming bitrate. So when you have simulcast enabled, you basically all your bitrate, incoming bitrate is coming from the high quality stream that you're receiving. If there's a few only forwards, one high quality stream and low quality stream for all the other participants, while the blue line is for the simulcast, for the non-simulcast case. I'm sorry, those are inverted. This is my fault. The blue line, the SFU is forwarding a high quality stream for all participants. So we have multiple data points. We make the participants vary from 1 participant to 10 participants, and you can see that it increases linearly with the number of participants if you don't have simulcast activated. And the yellow line is the efficiency, that how much gain you have if you have simulcast. So you gain 50% efficiency in a 3-way call. So one receiver is getting two other participants. It receives 2 other participants. You can conserve 50% of the incoming bandwidth. And as you increase the number of participants, this efficiency, this gain is increasing. Well, it cannot reach 100%, but it tends to be very high until it reaches a very high efficiency. So yeah, that was the simulcast stuff that we talked about. Thank you. So if you have any questions, I'm happy to take questions. Yes, please. Oh.
You referenced the motion vector optimization with simulcast. Just zoom in for a second.
Yeah, this is an encoding, a standard encoding practice. So you have to, when you do encoding, you have to find some motion vectors for the quantization process. And when you're doing simulcast, what the engine is doing, at least the VP8 engine, when you're doing native simulcast, you can reuse the motion vectors of the low quality stream to generate the high quality and the middle layer quality streams. So by reusing those motion vectors, you're optimizing CPU usage. At least that's one of the things that they must be doing. Probably they're doing other things as well. We haven't really dug into it, but that was the most obvious thing that so when we disable this motion vector reuse, the PSNR results for the simulcast case increased significantly. Yes?
Right now, the simulcast is only API on the client side, is only available on Chromium.
I'm sorry, only the client side?
The simulcast API on the client side is only available on Chromium.
No, that's I think we haven't experimented with it, but they have released simulcast for Firefox as well.
The API is the same.
The API is not the same. Well, everything is different in the API with respect to Firefox is adhering much more to the standards. What was called, which is I will leave that to your judgment if it's a good thing or not. But it adheres more to the standards, so that the API is completely different.
So in this case, we are performing on Chromium.
I'm sorry. Yeah, this is the performance with Chrome. Yeah, with Chromium, because we have built that, we have modified some stuff to test. Okay. Any other questions? Yes, please.
So when you stream to YouTube with Jiguri, do you have a particular optimization of the stream?
So when we stream to YouTube, we have to re-encode the stream, H.264 re-encoding. So whoever is the selected participant on the whoever is on stage on the YouTube stream will get high quality stream. Will be in HD, but you have to keep in mind that whatever is being displayed on YouTube is being decoded and re-encoded so that it's in H.264, so that it's H.264 encoded that YouTube understands, because we cannot stream VP8. Yes, please.
So, what kind of configuration for the machine do you use for this CPU impacts? Because lighter devices are going to have much harder time.
Yeah, we're using high-end MacBook Pros, essentially the same configuration. So on lighter devices, the impact will be different. Emil is shaking his head. I think he wants.
The difference in percentage is pretty low. So lighter devices that just have problem with encoding 1080p to begin with, and whether you have the lower streams, even if you'll be using motion vectors or not, that's not going to have a major impact.
There are other things that you can do also. There are other things that you can do instead of simulcast. So you have other congestion control features that you can implement on the server. Like last time, you can have other activity features. And on a mobile device, probably you want to configure your server to send local stream, not HD, or middle quality, like 360p, for example, not 1080p. Like this is configured on the server. Yes. Yeah.
So you said one of the optimizations you did is basically detecting that nobody is on the HD stream and not processing that on the server anymore. Have you considered even telling the client not to send the HD stream anymore?
Well, yes. Okay, I'm sorry. Yeah.
Right. So there's no way to do that. To put it well, there's no good way to do that. Currently, the way that by the standards, the way that you're supposed to be able to do that is to say send a TMNBR RTCP message to the sender and say, please don't send this stream anymore. I don't think any of the browsers support that right now. I think it was enabled in Firefox at some point, and then got disabled because I think it was breaking some Cisco stuff. the REMPs that Chrome uses as a way to signal currently available bandwidth do not allow you to distinguish between layers, between SSRCs, and to say this is how much bandwidth I give you for this layer, and this is how much you get for that one, and this is how much you get for the third one. You're just sending one bulk evaluation of here's how much bandwidth I think you have total. Okay, so that means that there's no RTP native way to say disable this stream, enable this stream. You're completely right. That's something that you ought to be able to do, but there's no easy way to do it with RTP now. So what that means that you're left with the only option to do that by manually the SDP and by removing layers from the SDP and triggering another set local, set remote description cycle. But keep in mind that this is something that has to be very snappy, because as active speakers change, that would mean that you might have to start or stop streaming certain layers, and doing a set local, set remote description cycle when that happens is something that is likely going to be very noticeable to the user. So at this time, we specifically are just waiting for the browsers to catch up and to start supporting this, but it's not currently possible in a way that we find satisfactory.
So I think in the spec, there's going to be a way to enable and disable encodings.
True, actually, right. However, this is only supported by Firefox right now, the RTP senders. We've been waiting for it to arrive in Chrome for a while. You're right, that you could, in that situation, you could use the data channel message to say, no, stop that stream. Perfectly.
Similarly, you consider like capping the max bandwidth on that connection, and then let Chrome decide that it cannot send the airstream.
That could potentially work. However, if you don't want to do it if you don't want to do it by touching the SDP, which I personally don't, that means that you have to basically send a lower REMB value and tell Chrome, you actually don't have enough bandwidth to send me all three layers. So here's how much you get. And I suspect that you might drop your highest quality layer if I tell you that value. That might work. What I'm not so confident about is how quickly you will be able to re-enable it after that. Because Chrome makes its own decisions about when to re-enable high quality. I guess it might be worth trying. That's the part that I'd be most afraid about, how quickly you'd be able to re-enable it, but maybe it would be, maybe it wouldn't be that bad. I don't know. Good idea.
Ramping up can be slow. If you drop your bandwidth estimation, then okay. Thank you very much. To take this actually, yeah.
Awesome. But it's hinged on a bunch of other things. So I suspect that if you try to submit a different way of doing it, they would say, no, this is the way that it has to be done. So wait for it.
Standards line, not just pull request.
Actually, there's a plan about standards.
Well, it is implemented by WebRTC.org. It's not exposing because these are the practices that the RTP center.
Yeah.
So it's a stalemate.
Hey everyone. Hi, I'm Armen Babikyan. I'm from Dialpad. I apologize in advance for the relatively unrefined details here. Oh, what is this for? Oh, the clicker?
You can, yeah.
That's all right.
Don't sabotage other people's presentations.
Uh-oh. I'll just use the arrows. How's that? Oops. This formatting didn't quite work out, but basically Dialpad. So we basically do modern business communication, cloud-based telephony. We've kind of got a storied history. There was an old Dialpad in 2005 that was acquired by Yahoo, had the same leadership team as my company. Then there was Grand Central, acquired by Google. And so a lot of the same people are involved in that, are involved in this now. And we were Firespotter Labs. We had Uberconference, that little thing right there. And that was in 2012. And in 2015, we launched Dialpad. Actually, I think it's 2014, but whatever. And then in 2016, we have grown our cloud-based telephony platform to have the largest pure cloud voice deployment ever. So how's that for a soundbite? So our original product was Uberconference. It's conference calling. It doesn't suck. It's product and user experience focused, and we run